Okay, it's 11 a.m. now in Ohio. Good morning, everyone. I'm Cherry Kubota. I'm the host for this series of webinars, um, Indoor Ag Science Cafe. I hope you are doing well. Um, December already. It's amazing how quickly um, the time passes. So this series of webinars is for CEA, Controlled Environment Agriculture, or Indoor Ag, Science and Technologies. That's why we name Indoor Ag Science Cafe. And then originally started by team we name OptimIA, which is USDA grant funded team led by Michigan State University. But we expanded scope, not just vertical farm, indoor agriculture, but also greenhouse and maybe high tunnels also. So now two additional groups join to support this extension effort, outreach effort, Advanced CEA group, and then also CEA HERB. So we are doing this monthly. If you are attending this first time, welcome to Indoor Ag Science Cafe. Uh, you're welcome to suggest topics too. So now we are looking at entire CEA technology. So I hope this is continuously serving for your needs and desire to learn and technology development. All right, so quickly advancing my slide. I just wanted to announce because this webinar today is Advanced CEA supported webinar. We are offering, this is not free one, so this particular one, because it's 14 weeks, 2 hours per week. It's not free course, but if you are part of the participating organization, that means Ohio State, Cornell University, Rutgers, University of Arizona, um, you have a discount price for this. But anyway, we are teaching technologies of controlled environment and strategies. It more introduction part, but I think it's a good opportunity to learn because not many universities, extension services can teach this type of technological or engineering basics. Okay, all right. So that's the little announcement. Now, today, we're gonna have Dr. Murat Kacira talking about greenhouse technology, specific greenhouse technology from University of Arizona. And then January 7th, we have economist um, uh, Dr. Gil Signorini, and then also Chris Higgins, for Americas, giving a co-presentation about status of industry, which is quite interesting. But just note that 10 a.m. start instead of 11, January 7th. And then more programs come up um, soon. So, okay. All right. So I'd like to have Dr. Murat Kacira. I'm gonna stop sharing, but the title of the presentation or the topic of the presentation is Wavelength Selective Covering and PV Photovoltaic Integrated Greenhouse System. So that's a really, really interesting area. So Murat, if you can start your presentation.
Well, thank you again, Cherry. I really appreciate the invitation. It's always nice to come to Indoor Cafe Series. We have, I believe this is my fifth time joining and presenting. Each time it's an exciting opportunity. So thank you for that. And thanks to everyone joining us today for the presentation. I hope everyone had an enjoyable holiday break. And now we're back to our uh, businesses and real world. So thank you for being here. This time, Cherry asked me to present about wavelength selective covering and photovoltaics integrated greenhouse systems. So I will discuss with you about the PV integrated greenhouse systems. And first, I will kind of talk a little bit about the expectations from the greenhouse systems side of the technology, and then I will kind of focus on the plant requirements, the expectations from the plant side of things. And then I will review briefly about some of the technologies available out there in terms of wavelength selective covering materials, particularly photovoltaics that are available for greenhouse systems integration. Then I will talk a little bit about some of the research activities we had as case studies and share with you our experiences and our observations. And then I will summarize some of the opportunities, of course, discuss some of the challenges that needs to be addressed from the research side of the spectrum, as well as technological maybe improvements needed towards future. And then hopefully we'll have some time for questions and discussions. So greenhouses are controlled environments, and they provide a barrier, a shelter to prevent the plant from external weather conditions. In the process, we optimize the internal conditions such as air temperature, humidity, and light, also other variables for optimal plant production. So the benefits to grow plants in greenhouse controlled environments is that we are able to achieve year-round production regardless of the weather conditions and seasonal changes. And this is especially important in regions where extreme weather patterns are experienced or we face limited growing season. Of course, within the controlled environments, we have the ability to control the climatic factors to optimize plant growth. So we're basically creating an optimal environment for plant production. Of course, in the process, we have the ability to reduce the risk of pests and disease occurrences as well. With greenhouses in controlled environments, we have the opportunity to increase yield, but also enhance some of the quality attributes with consistent quality, of course, achieved in a greenhouse production system. And that also brings the ability for an improved quality and also marketability of the produce in the market. So when it comes to greenhouses, greenhouse technologies, there are a variety of technologies available for us, of course, and the selection really depends on the expectation from that production and operation. There are low-tech greenhouse systems, there are medium-tech greenhouse systems and technologies. There are also high-tech greenhouse and technologies one can choose from. I believe the choice should really focus on, or the decision should be made in terms of adaptive technology selection, adaptive to local needs, the climatic factors, the consumer expectations, the local market demands, the capability in terms of investment, as well as the operational capabilities of the users and operators of these greenhouse systems. So we can present a viable and profitable, actually, business model. So when we consider greenhouses in terms of their technology level, in the case of low-tech greenhouses, such as the one that you see on the slide, there are simple systems used, hardware systems used, passive systems with minimal mechanical or electrical components, demanding for electrical energy. Usually natural sunlight is used, no lighting, supplemental lighting, maybe some ventilation and shading. So without advanced control, climatic control systems, in a system like this, in a low-tech greenhouse, again, depending on the region and climate, with the crops being grown, the range of electrical energy consumption can be somewhere between 2 to 10 kilowatt hours per meter square per year basis. In a medium-tech greenhouse operation, in this case, we kind of improve the hardware and technological capabilities with maybe some automated systems for climate control, electrical energy needed for lighting, maybe irrigation, supplemental heating and cooling systems. And then we have moderate level of technology integration to a medium tech greenhouse, but still limited to certain areas like crop management or energy saving devices. So in a system like this, our electrical energy consumption can range anywhere from 10 to 40 kilowatt hours per meter square per year. In a high-tech operation, though, we have highly automated systems for climate control, maybe advanced heating, ventilation, air conditioning systems, LED lighting, humidification, dehumidification, uh, uh, as well as automated nutrient delivery, some smart systems, artificial lighting maybe for year-round cultivation. In a system like this, in a high-tech greenhouse, our electrical energy demand can range anywhere from 40 to 100 plus kilowatt hours per meter square per year. So as you can see, there is that electrical energy requirement depending on the technology level. As we keep adding hardware and advanced control capabilities, then our energy demand also increases. From the plant side of things, the focus should be on plants also, because that's our main objective, to create the optimal environment for plant production. Strategically, of course, controlling the environment in a resource use efficient way, in a profitable way. There are nine significant parameters when it comes to plant growth, and that is affecting plant growth especially. Five of these fundamental significant parameters are above the ground level. They're around the aerial environment, air temperature, light, carbon dioxide, humidity, and air velocity. Four of those are on the root zone level: nutrients, water chemistry, root zone temperature, water, and oxygen. Among those nine, light happens to be one of the really, really significant and critical factor that really has a huge impact and effect on plant yield and growth and quality attributes, assuming all other factors are balanced and provided in a balanced way. In terms of plant production and growth, of course, humans have their kind of sensitivity to specific spectrum in terms of visible wavelength in the solar spectrum or light spectrum, but plants also really respond to a specific wavelength, and that is photosynthetically active radiation spectrum, which is between 400 to 700 nanometer range. And um, we can quantify, measure this light intensity within that spectrum. Those of us researchers, working in the photobiology area, they really pay attention to this metric in terms of plant yield and quality. And it's measured in terms of micromoles meters per second. As you can see here, the Mach-3 curve, which is a famous curve, summarizing the relative photosynthetic efficiency of plants based on the different wavelengths and spectrum. As you can see, there are some unique wavelengths where plants are responding to it more efficiently, and blue and red being one of those wavelengths in terms of chlorophyll absorption and the photosynthetic efficiency, but also there are other wavelengths that are important for plant production, and that's where the research has been really focusing on in terms of their effect on yield and quality attributes if they're strategically used. So there is the intensity of the light that is critical, but there's also the spectrum of light that is really important for plant production. And when you look at the literature, you would find a range of research focused on specific spectrums, their ratios in terms of how we can create a balanced crop, higher yielding and with good quality, desirable quality attributes. Of course, plants are responding to the light in their environment, to light, instantaneous light, but they respond to actually integrated environments. So plants are great integrators of their environment. So at the end of the day, they respond more to accumulated environment. So we need to pay attention to, of course, the minimums and maximums, instantaneous climatic factors. But at the end of the day, their response, yield, and quality is really correlated strongly to the accumulated integrated environments, and one of them being daily light integral. This is basically if we take all the photosynthetic active radiation during the light period or photo period, or when the sun is up, Then when we accumulate it, then we have the daily light integral. And there are target ranges, there are optimal ranges when it comes to different or variety of crops that are actually, some of them are listed here on this table. As you can see, some leafy greens and seedlings, maybe propagates, are demanding for smaller amount of maybe target DLI ranges, 4 to 10, maybe 15, 20 range. But when we kind of move towards more cut flowers or perennial crops, or maybe fruiting vegetables, tomatoes, cucumbers, and peppers, then the demand is further increased in terms of daily light integrals towards more 20 plus actually range for optimal yield expectation. And we need to also consider the availability of the daily light integral depending on the location we have. In this case, for the US, as you can see, for the whole year, the daily light integral availability is different depending on each state, as you can see. In the case of Arizona, we are favored by this factor here with more than 300 days of sunshine. Of course, that brings not only the light availability, but also the excess of that we need to manage in terms of creating the optimal environment. So when I hear about the sunlight being free energy for plant production, it's not really free. We have to deal with that to really balance it and create an environment that is optimal for the plant production. So those are the requirements on the greenhouse technology and side of things. And there are also requirements on the plant side of things, and that brings us to agrivoltaics. Agrivoltaics is the combination of photovoltaic systems embedded to agricultural applications, where we are able to achieve co-production of both food and crop production, agricultural practices, as well as electrical energy. So this is advantageous, of course, utilizing the same footprint, producing food and electricity. So we also prevent and limit the competition between the two in terms of land use. So the land use efficiency is increased. So when it comes to agricultural photovoltaic applications, agrivoltaics, we can consider open field agrivoltaic applications. As you can see, the structure can be interspaced PV or maybe overhead photovoltaics. In terms of solar tracking, they could be fixed systems, or maybe sun tracing or mobile access capabilities. In terms of transparency of the photovoltaic systems, there are semi-transparent materials available, or they can be constructed as opaque material. And as you can see, the applications can range from grassland farming to different kinds of cropping systems, field based cropping systems, as well as maybe horticultural crop production alternatives. But we can also consider agrivoltaics for closed systems, such as those with greenhouses, our main interest in this presentation. So PV greenhouses, depending on the objective and system design, these photovoltaic systems, again, can be stationary, or they can be installed and designed for with the ability to trace sun and enhance the electrical energy production capabilities. But these systems can also be opaque photovoltaics and semi-transparent and wavelength, also selective applications. So, and they can be used for both horticultural applications or different types of crops being grown, or maybe aquaculture can also be considered for greenhouse-based photovoltaic system integration. So what are the types of photovoltaic systems available? And they're being kind of researched. You look at the literature and with potential applications in controlled environment agriculture, greenhouse-based photovoltaic system integration. There are thin film photovoltaic systems. In this case, there is an active material with the PV technology, and that helps us to tune to transmit some of the wavelengths that is useful for the plants, and then absorb the wavelengths and convert that into absorb the wavelengths that are not usable for the plants and converting that into electrical energy. For example, organic photovoltaics, thin film organic photovoltaics can be an example of such thin film photovoltaic technology. And then there's this specially segmented photovoltaic systems with selective colored layer. In this case, these are composed of maybe conventional silicon or thin film uh, photovoltaics with spatially segmented PV cells. There are examples on this image here. The density of the PV cells are directly related to, or they have an impact in terms of the intensity of the light being transmitted. And there is a colored layer that is added, which is acting as a spectral filter to create or provide the wavelengths of light that is transmitted through this filter layer uh, uh, and then to reach to the plants, basically. And there is also concentrated photovoltaic systems, applications. These are also, they may be referred as also spectral splitting PV type systems. In this case, the incoming direct sunlight is spectrally divided and concentrated onto some high efficiency solar cells, ideally because the small focus area or focal area with commonly used concentrated PV systems, and then the wavelengths that are most critical for the crop production are transmitted to the plant, while the remainder of the wavelengths are concentrated on a high capacity, highly efficient PV cells to produce electricity. And then finally, there's also luminescent solar concentrated PV systems. In this case, these are the types of PV cells consist of a substrate coated or infused with a luminescent organic dye, or quantum dot technology is an example for this. And these are these have the ability to redirect incident light to mostly to the edges of the panel through photoluminescence. And then the light is collected by the fluorescent particles, are dispersed across the luminescent solar PV concentrators, and they're re-emitted to longer wavelengths. And then with this guiding to the PV cell and concentrated on the PV cell, they generate electricity. The PV cells are usually positioned along the edges of the panel as the light is guided through a luminescent material and layer to the PV cell to generate electricity. So these are the four main types of PV technologies that are mostly researched and envisioned to be a possible integration to greenhouse systems. So why wavelength selectivity for greenhouse production? Because it brings us the opportunity to control over a variety of light spectrums that is entering the greenhouse. We can optimize light for plant growth and photosynthesis, similar to our LED applications, right? For other indoor controlled environment agriculture systems. They bring the ability to reduce energy consumption for temperature control, not only air temperature control, but also ability to control plant temperature to a certain extent. And also potential savings maybe for water consumption in the greenhouse, not only for plant production, the plant water consumption, but also the water needed to condition the environment or for climate control purposes. And also against protection towards more maybe harmful spectrum in the solar radiation. And as I already mentioned previously, It brings us the ability to co-produce food and electrical energy within the same footprint of the greenhouse space, eliminating the competition between the two for land use. So if we review some of the literature in terms of agrivoltaics, particularly within greenhouses, over the course of maybe 2 decades and maybe more, you would see some unique systems, designs evaluated um, and assessed. As you can see, we see the systems, for example, using concentrate Fresnel lens-based glass, concentrating, focusing light onto a highly efficient PV cell array located inside the greenhouse to generate electricity. In some cases, we see opaque, traditional silicon photovoltaic panels installed on top of the greenhouse roof with some pattern um, to better understand light capture as well as light penetration to the crops and their effect with different types of crops, as you can see, from leafy greens to fruiting crops and berries. They have been evaluated in terms of the energy demand, efficiency, and system components, and partial shading effect and crop growth. As you can see, we have some variety of research already conducted on photovoltaics integrated greenhouse systems. Um, um, we have been also focusing on photovoltaics integrated greenhouse systems since 2012 with our initial effort around a really low-tech off-grid greenhouse system. As you can see on this image here, a modified high tunnel system with some climate control hardware embedded, integrated for cooling purposes in the greenhouse, growing mainly tomato crop as the main crop for this particular research application. Growing in a sand culture here, as you can see. And later, I believe we also evaluated a variety of leafy greens in the same greenhouse project. Our focus here was to really understand the capabilities in terms of creating an environment for the plant in an off-the-grid greenhouse solely powered by solar photovoltaics, and compare that environment and yield outcome in a greenhouse where the greenhouse is powered by a grid connection. As you can see, our student back then, master's student Polly Zhuang, performed this research. You can see the yield of tomato crop. These are cherry tomatoes. In terms of kilograms per meter squared, they're very comparable to each other. And in this research, we also demonstrated the ability to produce the electricity, the demand that is met by the off-grid photovoltaic panels designed particularly to meet all the energy requirements of this greenhouse system. And here are some of the crops that were grown also, leafy greens in the same off-grid photovoltaic greenhouse system. So our objective was really, what if we have communities remotely located, remote from electrical grid, and without immediate access to resources, electricity, and fresh produce. This would be an alternative technology platform or a technology platform for the community members to produce their own fresh produce locally in their communities to consume within the family or maybe presented to the market. So that was mainly our objective and interest. I believe later on, in addition to solar photovoltaics integration, we also evaluated a liquid organic fertilizer that was produced by waste food materials. There are some possible applications for such technology in an off-the-grid greenhouse. Again, this was also our objectives, as I mentioned, maybe in remote locations, maybe disastrous zones where you need some fresh produce provided to the community members, maybe remote indigenous communities that are challenged in terms of resources, maybe water, access to potable water, or maybe access to fresh produce. That is the case, for example, in the state of Arizona here with our indigenous communities. Actually, we have a National Science Foundation project that is focusing on solar powered food production systems, greenhouses, as well as potable water presented to community members through solar-powered nanofiltration systems, using this model of the grid greenhouse system as the technology platform, but also other opportunities, maybe military applications in remote, maybe forward operating bases, either with greenhouses that you see here, producing the food, maybe some solar photovoltaics used on top of the structure, or maybe a shipping container type of systems using photovoltaic panels to power the greenhouse. Actually, we have a student capstone design project that worked on this shipping container-based solar powered system from Biosystems Engineering Department. And the system is right now operating at Biosphere 2 facility. But the photovoltaic system can also process maybe unsafe water and create a safer water for drinking purposes, but also for the horticulture, for the agricultural production applications in that controlled environments, maybe desert climates, or maybe Arctic locations where the energy and food production is really challenged in terms of the resource availability and access. That was our initial project, as I mentioned, and later another master's students in our lab, Ming Lee, focused on luminescent solar concentrated photovoltaic system, a greenhouse here. This project had the fame of being called as Pink Greenhouse. I really enjoyed that. Here, this was also a collaboration with Dr. Kubota here when she was here at the University of Arizona. Her focus was more on the plant response to this technology. In my case, my focus was more on the electrical energy consumption and maybe some water savings and light use efficiency side of the technology and system side of it. And it was a collaboration with an industrial partner company. As you can see here, so the control greenhouse and the treatment greenhouse, we have tomato growing. These are smaller size, TOV size tomatoes grown in the greenhouse in both greenhouses. The LSC integrated greenhouse was fully covered in terms of the covering material. On top of the greenhouse, it was a glass with a luminescent solar concentrated PV cells embedded in the material. These were bifacial, sorry, PV cells generating electricity with the light incident from outside of the greenhouse to the PV cells, but also those reflected from the below the panels to be able to generate electricity. We also covered the gable ends, end walls here with dummy covering materials, dummy cells, no electricity production capabilities, to kind of envision a greenhouse that is fully covered by this material. As you can see, the comparison between the yield in both greenhouses, of course, because of the nature and the shading of this structure, we see differences in terms of the yield pattern. Even though the light intensity when it comes to the solar radiation was reduced about 45, 46% or 47%, the yield reduction was not equally reduced. As you can see here, I believe it was around maybe 30% reduction. So with this type of technology, that rule of thumb, 1% light, 1% of yield is slightly shifted towards a different kind of level. As you can see, depending on the light available for the plants in the LSC integrated greenhouse, the light use efficiency is actually greater compared to the light use efficiency for the plant grown in the controlled greenhouse. This is the amount of light received and the corresponding yield outcome achieved uh, under this technology. So later on, we also focused on strategic covering of a greenhouse roof with different ratios of photovoltaic systems. As you can imagine, a fully covered roof can also present challenges in terms of light transmission, light availability. So what if we change that in terms of its deployment? So here, Kensako Okada, another graduate student in our program, did a simulation study by predicting plant growth. In his case, it was lettuce crop, predicting the crop yield, and also predicting the energy, electrical energy outcome, production and consumption as well, to gauge what might be the economic factors under different range of various roof coverage, PV coverage ratio on the roof of the greenhouse. In his case, though, he evaluated particularly three cases. These three cases are 100%, 50% coverage on the roof, growing lettuce during the summertime, basically, June to September, I believe. Either we are growing the crop, for example, case 2 and 3, or not growing the crop during that time. But the remainder part of the year, the roof coverage was changed from 0% to all the way 100%. So this allows us, actually, a study like this allows someone to really look into yield outcome capabilities. As you can see, those are the lines indicating the crop yield under these scenarios versus the electrical energy production capabilities in terms of kilowatt hours per meter square per year basis. So with this type of data, then one can better judge in terms of the profitability margins or maybe the viability of such technology application. And later on, another student in our program, sorry, the name is wrong here, but Rebecca Waller, a PhD student, performed a study on organic photovoltaic films embedded to greenhouse roof as a covering material. Um, in this case, we literally covered the roof of the greenhouse, half of it actually, with these organic thin film organic photovoltaic materials. I believe if you look at the literature, this is one of the largest um, uh, organic photovoltaic film deployment in a research setting. I believe we covered about 60 meters square greenhouse roof in this case. And we not only looked at electricity production capabilities and the degradation of the films, but also compared crop growth, tomato crop again, under organic film versus non-organic or open control roof greenhouse cases. As you can see, the yield is still comparable. Of course, some reduction of the yield in the case of organic photovoltaic film installation. Um, um, uh, However, when we look at cumulative yield and cumulative photosynthetic active radiation, you can see that steep slope for the organic photovoltaic film. Again, this is an indication of the light use efficiency information being much greater in the case of organic photovoltaic film to control. So what this really means is that, yes, we are reducing the light, but we are achieving some, acceptable level of crop yield and production. So this information can be used in a way that we can maybe think about strategic deployment patterns, roof coverage ratios, maybe different crops. What would be the installation pattern and design, where we can deploy these films outside or inside the greenhouse. In the case of this particular project with organic photovoltaic films, our observation was also that they were more efficient under diffuse light conditions. So compared to a direct light um, um, uh, incident on organic photovoltaic films. So in this case, one can consider maybe deploying organic photovoltaic films inside the greenhouse, um, so we can generate higher level of, larger electricity production capabilities, but also maybe we can protect the film from harsh and dynamic climatic conditions that are mostly present to the panel when they're deployed outside. Another strategic maybe deployment can consider dynamic operation of these thin film photovoltaic panels, maybe as a shade curtain at the same time, partially deployed some time of the day or year to basically create more dynamic control capabilities. Another research focused on designing a low-cost microcontroller-based climate control system with Arduinos for a high tunnel system equipped with a fan to really help controlling the environment slightly better compared to a non-ventilated greenhouse system located in the Navajo Nation here in Arizona. As you can see, our student Calder designed this greenhouse PV integration system, but mainly on the climate control system. Uh, uh, a system like this can enable an operator with remote access to this greenhouse, which was actually located further away from their house. So we did, control capability around air temperature and maybe irrigation system control applications. These are some of the photovoltaics embedded greenhouse systems that we worked on, but also there are wavelength selective, non-electricity producing green covering materials also available. In this case, this was a collaboration with a industry collaborator, as they have this near infrared spectrum absorbing capability for their material that allows us to reduce the need for electrical energy for cooling, for example, or also conditioning the plant in terms of temperature control. With the ability to potentially reduce the water consumption as well. As you can see, in our case, we kind of evaluated the production of 9 different crop rootstocks for tomato crop. There was no control in this case. It was just for us to assess, the yield and quality capabilities under this roof covering material, but also some of the observations for leafy greens, as you can see in a control greenhouse in this case, with acrylic double layer, acrylic clear, acrylic material versus this NIR filtering covering material. As you can see, in terms of yield and quality, they were really fairly comparable in both cases. There are also quantum dot based applications when it comes to wavelength selectivity. So depending on these nanoparticles and quantum dots, their concentration, depending on their concentration, it really affects the light quality or the spectrum and light penetration. A graduate student here at the CEAC Morgan evaluated this technology from Ubiquity company in terms of yield and quality outcome of tomato crops grown in these greenhouses. This is the quantum dot covered greenhouse, and compared to a control greenhouse, the main covering material in this case was an ETFE covering on top of the quantum dot film greenhouse. So the quantum dot is installed as an inner layer to further change or alter the spectrum. As you can see, their observation and the study really indicated that the spectrum in the 625 nanometer range was more effective in offering enhanced yield and quality with this quantum dot film technology. I believe they had two different kind of quantum dots. One is in the 620 range, the other one is in the 650 range. So kind of um, summarizing some of these technologies and observations and those from previous research as well. There are some opportunities with wavelength selective greenhouse cover, but also there are challenges. So in terms of opportunities, in terms of wavelength selectivity of greenhouse covers, we can optimize light spectrum for plant growth. They can offer energy saving capabilities, maybe managing the heat load in the greenhouse and the crop as well. They can be customized in terms of crop needs when it comes to light requirements, environmental control capabilities by adjusting the spectrum, of course, for the incoming sunlight, the wavelength control capabilities, so we can create ideal conditions, but also challenges. They bring challenges, of course, the high cost and manufacturing complexity of these wavelength selective covering materials, their durability and maintenance is a concern that needs to be addressed, and the light spectrum also control. How can we filter out the certain wavelengths with the ability to adjust the spectrum, for example, dynamically depending on the season, the day. So those are kind of the complexities and challenges that needs to be addressed. Also, their integration to an existing technology, greenhouse technology, that needs to be considered as well. In terms of photovoltaics integrated greenhouses, CEA agrivoltaics, the term that I like to use, opportunities, they offer the dual use of space, agriculture, and photovoltaics, of course, land use efficiencies enhanced with the ability to reduce maybe energy costs for the greenhouse operation. They can offer climate resilient, more sustainable agricultural practice in controlled environments. They're potentially applicable for grid contribution and maybe localized microgrid type of electric generating capabilities. Of course, the challenges are the light transmission for crops. Anything that we place, any structure that we place on top of a greenhouse as a covering material is kind of counterintuitive, right? For towards the original purpose of a greenhouse system. However, if strategically introduced and designed and incorporated, then we have some opportunities there. So that needs to be considered in terms of what kind of cropping pattern, cropping structure, architecture, as well as deployment of these covering materials or photovoltaic technologies. A challenge is the high initial capital investment, something to consider, the maintenance and durability. Sometimes, depending on, again, the technology level, their efficiencies, especially, for example, organic photovoltaic films, are somewhere between 1 to 3% in actual outdoor deployments, even though the ratings are usually 6 to 8%, maybe 10% in laboratory settings. Their burn time can be really fast in terms of degradation of the panel and efficiency when deployed outdoor conditions. The durability of the material needs to be kind of considered. The lamination quality, especially when it comes to thin film photovoltaics, needs to be considered. Of course, the impact of shading on the certain crops are kind of must be considered. I pointed out some of those in terms of the patterns of deployments. And technology compatibility also. Again, photovoltaic systems and the greenhouse systems, we have to have a good marriage there in terms of their integration. Wavelength selective covering materials combined with photovoltaic systems, opportunities, again, enhanced efficiency, wavelength combination with electricity generation is a positive. The better light distribution, environmental benefits, we can further contribute to sustainability by reducing the carbon footprint there. And also with maybe light management capabilities. Of course, the challenges, complexity of the integration with such technology, the cost, of course, needs to be considered. The balance between the light and energy production must be considered, and the profitability around that also should be considered when it comes to such technology applications. I really believe that wavelength selective covering materials and photovoltaic systems integrations are providing some unique opportunities when we consider greenhouse systems integration. I'm sure there will be more research conducted on this and performed. It will depend on the location, the climate, the market, profitability. Again, the technology selected. Technology is advancing, becoming more advanced and cheaper and lower cost. And with durability also embedded, I believe we will see some exciting opportunities with wavelength selective covering materials with PV integration. I also wanted to share some selected literature and references for you to consider as part of maybe your research. With that, I would like to also make two advertisements for those of you maybe interested in joining us for an intensive hands-on workshop for greenhouse hydroponics. We have one offered in January 10th through 12th with Dr. Hooks from our team here, the University of Arizona. I share with you the link here. Please join us if this is an interest for you. The seats are limited to 25, 30 participants in this case, but we also offering our 24th greenhouse engineering design and crop production short course in a special year 2025, which is our 25th years of anniversary for the Controlled Environment Agriculture Center here at the University of Arizona. So we will have our short course during March 26th and 28th. In this case, we have opportunities also for our industry collaborators and partners to join us as exhibitors for the 3-day program. Our emphasis for the short course in March will be around circular controlled environment agriculture systems. I believe that also fits well with our presentation today. So with that, I would like to thank everyone once again joining us, and I hope we have some time for maybe a Q&A. So thank you again for the opportunity.
All right. Well, thank you so much, Murat. I really
Thank you.
appreciate. Excellent presentation, very comprehensive. Thank you so much.
Thank you, Chair. Appreciate it.